As I say, I'm not going to get bogged down in C++ code issues. I do a workshop in which we do how to introduce code to OpenSees. And from like 8 o'clock in the morning till 4 o'clock in the afternoon, we're just basically going through, well, from 8 to 1, we're just talking about how to program in C and C++. From about 1 to 3, we go through, well, here's the theory I want you to implement. Go make these changes to the code. And then for the last half hour, they just put it into OpenSees. The hard part is actually explaining them how to use not just C++, but Visual Studio as well. That's the hard part. Implementing, putting it into OpenSees is trivial. So, as I say again, as I mentioned yesterday, commercial codes are complex. They're closed source. You can add element to material routines into these commercial codes, but you can't add the other things, integrators, solvers, solution algorithms. As I showed you yesterday, integrators, they can have a really important result on what the response is going to be. They're slow to change as hardware changes. The industry people in San Francisco that are looking to use OpenSees, they're looking to use it just because of the performance. Andreas, he showed you his little wind and solar analysis that they did at Rutherford Machine. That was taking them days to run when they were using Perform. They were able to run it in like an hour and a half when they ran it in OpenSees. So they started running all their different models to actually get a final model using OpenSees, and then they were able to run the thing and Perform to get it by the code checkers. The thing is, when you're writing code as a graduate student, you don't have to understand every class in OpenSees. You only care about that class that you're going to implement. If you're going to write a new material or you're going to write a new element, only look at the material and the element classes. Don't go off and try and figure out how the analysis is working to figure out how it's calling your element. You don't care. Okay? All you have to do is meet the interface for an element or material if you're introducing an element or material. And the element and materials, they're the complicated interfaces. If you look at the transient integrators or a solver, AX equals B, their actually interfaces are a lot easier to implement. So these are all the abstract classes in OpenSees. And if you want, you can introduce your own version of any of these classes. You can introduce your own new recorders, constraint handler, numbers, elements, nodes, materials, anything you want, you can introduce your own. The code is set up to accept any other contribution. So the abstract and concrete classes. So the point here is you have to provide some new concrete class. You have to provide your own Uniax material. Never start with a blank, empty file when you write code. Always start with something that either resembles what you have or is simple enough that you understand you can take it out and just you just take out the code part and just fill in the blanks. So this is how it works. When OpenSees is running and it comes across, say, a material that it doesn't know, you've got your own Uniax material, and it comes across that in the command line. OpenSees just doesn't exit. Before it exits, it looks in your directory or in the load path to see if a certain DLL exists with that material name. If it finds that DLL with that material name, it will load up that file, and it will search that file for a specific routine. If that routine is there, that's the routine that gets invoked by the command line. I'll show you an example of what that actually function is in the code. And only after that will it actually fail. If it can't find the library or it can't find the procedure in the library, the code is going to fail. So basically, here I'm just showing you a little example. So I have this script that's using elastic CPP material. When I run it, it fails. Could not find the execute the material. So to add a new class to OpenSees, you must meet the API. So you're going to add a new Uniax material. You have to meet the Uniax material API. So that's really the only class you have to look at. While the code OpenSees is written in C++, if you have code in C or Fortran, you can use it with OpenSees. It's actually quite a simple process for elements and materials. Take them that work for existing codes and put them into OpenSees. Elements and materials, they're just given a displacement, give me back the tangent and give me the resisting force. That's the finite element method. The materials are here's your strain, give me the stress, give me the tangent. Again, that's materials, that's the finite element method. They all do the same stuff. So it's quite simple if you have this code to wrap the C++ around it and call your function. If you need help with that, I can usually do it in a couple of hours to put a new code into OpenSees. So this is the Uniax material class. So I just want to quickly show what some things are. A little bit of C++. This funny thing that says virtual before it in the abstract class, that is a method that you can provide your own implementation of. You don't have to take the default. If you have a virtual and an equals 0, that means it's a function that exists in the abstract class for which there is no definition. So if you must then, as a programmer, actually provide some implementation. If you don't provide an implementation and you try and link it with OpenSees, it's going to fail. It's just not going to work. So you have to provide some implementation if you have an equal 0. Some of them don't have an equal 0, so you don't have to implement anything here. For example, this is a set response and get response, or what's called by the recorder. I'm going to, all elements, the base class will understand, give me the stress or give me the strain. So if you're happy with that, you leave these methods alone. If you're unhappy with it, you want your material to respond to something other than stress and strain, that's where you'd put it. You'd modify the code a little bit there. Just copy what's in the base class and make the modification. And for the parallel stuff, if you want your elements and material to run on SP, you have to implement these send and receive self methods. Basically, you have to send the state of your material from one process to another. So you've got to be able to repeat your material that's in some configuration or some state on one process, and you have to be able to repeat it on another process so it can take up, the computation can take up where it left off. I would say never start with an empty file, always start with something that already exists. So like we did yesterday when we downloaded the examples with using SVN, we can download what's called the developer trunk from OpenSees, which contains the source code for actually adding new elements and materials. If you're Windows users, I like to use Tortoise SVN. So when you download the developer code, you get a number of directories. One important directory is the core. The core directory contains all the abstract classes in OpenSees, because they're actually required to build the DLL on Windows. These other directories contain example implementations. For example, there's a new recorder in there, a new integrator, new solvers. So if you just want to see examples, there's also materials and elements. For the materials, we actually have C++, C, and Fortran examples. These C and Fortran examples are actually meeting an API that we provide. So if you want to write a new C or Fortran routine that meets our API, it'll actually automatically work in with OpenSees. You don't have to provide any additional code. But if you have additional code, existing code, you do have to provide some C++ code. We have to modify it a little bit for your element and material. But as I say, you can write to our API, and the C or Fortran code will work. So once you have your code, putting it into Windows is a 24-step process that I usually say even Stanford students can follow, but they can. As I say, it's 24 steps. If you follow these steps, you will get a working DLL on Windows that will work with the OpenSees executable. I'm not going to show them now, but in this slide, if you download it, it basically, actually, I'll get there in a minute. Yeah. So here's this elastic PP CPP class. And these are how it's defined in the example. And when we have our code development workshop, basically all the students have to do is come in here and change these. Anything in red, they basically have to go in and change for their particular material that they want to implement. And that, as I say, you guys can do that too. As I say, you give it a new material name, and each material is going to have a different number of input arguments. You have to specify what the input arguments for your specific material are. And then down here you have to store those materials. Then you go to the CPP file, the implementation file, and you start implementing the code. And most of them are, these what are called constructors are very, very simple to implement. You take whatever the arguments are and you just assign them to the variables. And then any other additional state variables you have in your code, you just initialize here in the constructor. The hardest method to write for a uniaxial material is to set trial strain. Given the strain, you have to set the trial stress and the trial tangent within the material. I picked a really easy material to implement. As your material gets more complicated, so does the source code for here. And as I say, writing the source code is not the hard part. The hard part is getting the theory correct. But once you have the theory right, spend your time on the theory. Don't start coding it up before you come up with the theory. You'd actually be surprised at the number of people who just sit down and start writing code before they've laid out just exactly what they want to do. So these other methods, if you implement it like this, where you're using this trial stress and the trial tangent inside the set trial strain, you basically leave alone. And then this is that method I say that when OpenSees loads up the DLL, this is the method I have to go looking for. This is the method that is going to parse your command line for all the different number of arguments you want with your material. And it's pretty easy. What I like to tell people to do, if you want to get kudos for your work, just put up who wrote the code, so that when other people run this code, they're going to see your name. As researchers, if you want, you've got some paper that's associated with this element of material, and you want people to reference that work, you might spit up a message. And if you find this useful for your work, please cite this reference. So you can do that. Just do it in this function right here. When it's called once, it'll come across the screen when you run OpenSees. So instead of seeing OpenSees UC Berkeley, you see OpenSees UC Berkeley, and then your message comes across the screen. So you can make OpenSees kind of look like your own. So here's where I actually parse the data. So this one, it's getting that material tag, so it's getting an integer. We can also get double arguments. This material has 3 arguments. The first argument is the tag, and then there's 2 doubles. So the first one, num data is set to 1, I'm getting an input. I'm getting an integer input. The second one, I'm getting a double input. And then I'm just calling my new constructor. As they see, and Fortran procedures can also be used. So I'm not going to go through it, but I do throw the 24 steps to building a DLL. Just, click here. This is foolproof. I won't mention what I would normally mention again. It's bulletproof, Wendy. So that's the example. So now I can show you how you do it in Unix. As I say, it's 2 minutes once you have the code. You download the code. You CD to the directory you want to go, and you just type make, and boom, you're done. So let me demonstrate how easy this is on Linux. download the code, you'd see you'd have these couple of files in your directory. If I OpenSees, basically the transient integrated trapezoidal wasn't found. So as I say, you just type make, and then you run it again, and your code's in OpenSees. So as I say, once you got the code, running it with OpenSees is, it's simple. The hard part is writing that code. And the harder part still is coming up with the theory. They give PhDs to students who come up with new elements and materials. So it's not a trivial matter. It's good programming practice, though, for students to take existing elements and materials that are in the literature and just implement them. Either there's, just redoing the quad element or the, it's practice with that. If you want to, practice programming. To become a better programmer, you have to program. Just going through a class, not doing the exercises, or going through a class and not doing any coding for a number of years, you're just going to lose the ability to program. So you have to program. So with that, I'm done. Any questions? Yep.
Anybody can add code?
Anybody can add code. To the repository, if you do come up with code and you want to add it back into OpenSees, we pretty much accept anything. All you have to provide is the CPP, the H file. We need documentation from you on what the command is. Some theory would be nice. And we also request that you provide us example scripts that show that it can run, so that we can verify that the results you're getting are the same as the results we get when we build it on the different platforms. As I say, we build it on a number of platforms. We need to get the same answer on the different platforms within a certain percentage. I know we're not going to get the exact same answer to the same decision, but within 1%, we want to make sure we're getting the exact same answer as you guys are getting. So you have to provide us scripts that we can run that will demonstrate that, and that demonstrate that the code you've given us is matching what's in your papers or your dissertations. So that's basically what we request. But if you have that, we pretty much accept anything. We're not the arbitrators of, this is bad code, or we don't look at the coding style, though others will if the source code goes online. So just remember, everybody in the world, when the code goes into OpenSees, gets to have a look at how you write code. But we do encourage students to send us in their code. Professors find that, if the students give them the code and they just keep it around, eventually they lose it. When you give it to us, it is put in a repository. That repository is backed up. So if you need to get some of the students' old code, we can give it to you, or you can download it yourself. You don't even have to talk to us. It's available. Any other questions? Michael?
And I would say you should look at the code that's there and make sure you're not duplicating something that's already in the repository.
But
that happens a lot.
Yeah, but it's also good practice. Well, yeah.
Yeah.
If it's duplicate code, we probably won't put in. But it's good. It's good practice for the students to program too. They need to be able to program. They can. Sometimes you just can't start off on the most complicated thing in the world. Let them implement their own trust or something.
Yeah, I don't disagree. I'm saying don't ask to check it in if it's already been implemented and checked in.
Okay. That's right. We're not going to have 100 trusses in OpenSees.
Yeah, the only way to understand how an element works is implementing an element. I don't believe that if you don't implement an element, you don't know how an element works. You can do it.
I was just back from a workshop in China, and they want, as part of their final known courses, they're having the students program elements and materials, like simple ones, but they make them go through the plane stress element. They'll have them develop the code, write the code, check that it works.
But we don't need 4 plane stress.
No, we don't need 4 plane stress.
Do the same thing.
No, Michael, we don't. Okay. Any other questions? Comments, observations? Documentation is the hard part. Getting people to give me their documentation is pretty hard. Some people in this room are very guilty of not documenting all the code that's in OpenSees. Because I don't have total control. Question?
For now, whatever works on sequential also works on
No. There's a lot of code that gets checked in where the send self and receive self methods aren't implemented. They have to be back, they have to be implemented. The thing about SP is, as I said yesterday, the sequential one is to be tested. Pretty much all the bugs in source code are out. If there's something wrong with somebody's theory, that's still in the code because they've coded it to the theory and I can't check whether the theory is correct. I can't spend time going through everybody's dissertation to find out what's right or what's wrong with this theory.
Does UP element works in parallel?
The UP?
Yeah.
Yeah, Pedro plays with parallel all the time.
And also PDMY in serial?
Yeah. Yeah, and actually, I second what you said, these solver maps makes a huge difference. So that's why I ran sequential runs, but using the parallel version.